Okay, in the previous video we have learned semigroups and the monoids. Okay, so in essence, semigroup is a set with a binary operation uh, that is associative. Okay, and monoids is a semigroup with the identity element. Now we define groups. So here's the definition. Let G be a non-empty set. So this is a set. And let's say we have a binary operation. Binary operation. Operator. Which we just write like, instead of writing like this, A star B, we just abbreviate this to write AB. Okay, so this is just A multiplied by B. Okay, then we say G is a group if the following conditions are satisfied. Okay, first, for all pairs of elements in G, we have AB is in G. So this is a closure condition, just like in a semigroup. Closure. And second, for all triples in this, we have associativity. AB times C is equal to A times BC. So this is associativity. And the third condition, there exists an element in G such that for all elements in G we have EA is equal to A. So this is identity element. And fourth is for all elements in G, there exists an element which we denote by A inverse, which is in G, such that A inverse times A is equal to the identity element. So this is the requirement for inverse element. Okay, as you can see, the first two conditions defines, this is just the same as the semigroup. And the first three conditions, if they are met, then it is a monoid. So if we add the last one, then this group, set G is a group. Okay, so for every element there is its left inverse element. Okay, but as we have seen before, together with condition 3, condition 4 specifies this inverse element as actually not just left inverse, but it's also the right inverse. So that is, if we have all these conditions, we know that EA is also is equal to AE, which is equal to A. And for the inverse elements, we have A inverse times A is equal to A inverse is equal to E. So we've seen this before. And also you should prove that the inverse of an inverse is the original element. So A inverse inverse is equal to A itself. Okay, next let's prove this interesting theorem. Let S be a semigroup. So that is, S is a non-empty set that has a binary operator, and that binary operator satisfies closure condition and associativity law. Okay. Then suppose for all elements A, B in S, if there exists elements X and Y in S such that A AX is equal to B and YA is equal to B. Okay, so suppose this condition holds. Then S is actually a group. So let's prove this theorem. So since S is assumed to be a semigroup, all we need to show is the existence of the identity element and the existence of inverse element for each element of S. Okay. So let's do it. Let's say let A be any element. Then by assumption, there exists some element in S such that EA is equal to A, right? So that means, okay, let's pick this condition. So there exists some element Y such that YA is equal to B. So in this case, this A and B happens to be the same element. Okay, so that's possible because we are saying A, B, they are any element. So A and B could be the same element. So for A, there exists an element E such that this holds. Okay. Now we show this E is indeed the identity element. But at this point, this E may depend on the choice of A. We need to show that the same E also satisfies the same equation, such as EB is equal to B, and so on, for any element B. So this E and this E should be the same E. Okay, so that's what we are going to show now. So let's see, let B be any element. Be any element of S. So by assumption, there exists a so by assumption there exists some element, let's call it U, such that AU is equal to B. Okay, so in this time we used this condition. Okay, so then EB is equal to, so using this B is equal to AU, but using associativity, this is EA. You know, S is supposed to be a semigroup, so this is okay. But EA is A, right? Because we're assuming this. But AU is equal to B. Therefore, EB is equal to B. So, but this B was any element. So, therefore, therefore, for any element in let's say A in S, we have EA is equal to A. Therefore, E is the identity element. Okay. Now, next we prove the existence of the inverse element for each element. So by assumption, for all elements C in S, there exists C prime such that C prime C is equal to E. So in this case, let's see, we used this A and B to be C and E. Okay, we put this A as C and this B as E. Okay, E is the identity element we have just got. So so C can be any element. E is some unique element. So given these two elements, there exists some element Y. In this case, we call it C prime. So this is satisfied. So this means C prime is the left inverse. Left inverse of C. So so this left inverse exists for any element. So this S satisfies all the axioms of a group. So therefore, S is a group. The next theorem is also used to distinguish a group, but in this case only for finite groups. Okay, so let S be a finite semigroup. The reason why we need this will become apparent when we do proofs. Okay, with cancellation. So this cancellation means this. Okay, let's say we have ABX in S and AX is equal to BX. Then this implies A is equal to B. And also, if A, B, Y are elements of S, and if A is equal to Y, B, then A is equal to B. So if these two conditions are satisfied, so this means in this case we can cancel the common element from the right, and we can cancel the common element from the left. Okay, so if we cancel x, then we have a equal to b, and if we cancel y, we have a equal to b. So then S is a finite group. Okay, let's prove this theorem. For this proof, we use the previous theorem. So we show that for any elements a, b in S, there exists some x in S such that ax is equal to b. And also we show that this such f y exists. Okay, we show this. Okay, so let a and b be any elements. Okay, since here it becomes apparent that why we require the set to semigroup to be finite. Since S is finite, uh, suppose there are n elements, so we could enumerate all elements of S, like S1, S2, and up to Sn. Okay, and now consider elements such as AS1, AS2, up to ASn. Okay, so again, these are n elements. And these elements, so these elements must be distinct. Because if if ASI is equal to ASJ, suppose I and J are different, but by the assumption, this implies we can cancel A, so ASI is equal to SJ. So I and J cannot be different. So if they are so but by the contrapositive, if SI is not equal to SJ, then ASI is not equal to ASJ. So all these n elements are distinct. So they're all different from each other. So therefore, B, this element B is equal to ASI, let's call it ASK, for some K. Okay, so one of these numbers must be equal to K such that this holds. Okay, so this SK is the X we are looking for. Okay, and similarly, we can consider S1A, S2A, and so on. So these are all distinct by the same argument. So B is equal to S, let's call it L, A, for some L. So we have these conditions, and by the previous theorem, S is a group. In particular, it's a finite group. You know, the finiteness is required because of this argument. Okay, we have to be able to enumerate all the elements of S. Otherwise, we cannot use this logic. Okay, and that's it. Now let's see a few examples of actual groups. And let's say first example, the set of rational numbers except for 0 together with multiplication. Let's see. Multiplication. This is just an ordinary multiplication of numbers. then this is a group. So let's check that. So first of all, let's say if we have two rational numbers that are non-zero, because we exclude 0, then a times b is a rational number, right? So that's okay. And of course, this is just an ordinary multiplication, so the associativity holds. So that's okay. And the next one, this 1 times any rational number is equal to that rational number. So this 1 is the identity. And also, for every element in this, we have 1 over a. 1 over a is, of course, a rational number. Since it's non-zero, we can just calculate 1 over a. Okay, and 1 over a times a is equal to 1. 1 is the identity element, so for every element there is an inverse element. So this is a group. And second example, the set of integers under usual multiplication is not a group. So this is not a group. And this is easy to see because, for example, for 0, there is no inverse element. So 0 times any element cannot be equal to 1, right? So as long as a is an integer, or any number actually, but if you multiply by 0, it must be equal to 0. So it cannot be equal to 1. So there is no inverse element for 0. So for this one fact, we can see this is not a group. However, the same set of integers, but with addition instead of multiplication, this is a group. Let's see this. Obviously, for any integers, a plus b is an integer. So the closure condition is satisfied. And then associativity, so first a plus b plus c is equal to a plus b plus c. So associativity is okay. And what about the identity element? 0 is the identity element. So this is equal to this. And what about the inverse? So for every element a, we have negative a, which is equal to 0. So we always have the inverse element with respect to addition. So all these conditions are met, so the set of integers together with addition is a group. Here's another theorem that characterizes groups. Let G be a group. Then we have the following. First, cancellation. That is, if A, B, X are elements of G such that AX is equal to BX. Then a is equal to b. So that means we can cancel this x from the right. And also we have cancellation from the left also. So of course a, b, and y are elements of G. Then if this equation holds, then we have a equal to b. Okay. Also. And second, unique solution of equation. So that is, let a and b be elements of G. So then ax equal to b has the unique solution. That is, x is equal to a inverse times b. And also we can solve ya equal to b by multiplying the inverse of a from the right. So y is equal to b a inverse. So in this case, this one is the unique solution of this equation. Okay, the proof is very simple. Okay, so if we have ax equal to bx, then multiply x inverse from the right. So we have x inverse from the right. Then by associativity we have this. But x times x inverse is the identity. But multiplying by identity doesn't change the element, so we have a equal to b. And we can similarly prove this one too. And second one, that was the first one. If we have ax equal to b, then multiply a inverse from the left. By associativity, we have a inverse ax and a inverse b, and this one is ex, but ex is equal to x, and that's it. And we can similarly prove this one.